All right. Good afternoon. Any question before we start? So we continue on stress. If we have something like this bar, which is under axial load of P, we would like to define the stress at point A. So stress is defined as force dividing by the area. So when we are talking about the area, means we should specify the plane in which point A lies in it before we define the stress. So as we talked on Thursday class, we can pass infinite plane through this point, like this, or some other different plane. After we define the plane, we can define the stress term for point A. So in general, you can pass three perpendicular plane passing through a point, like point A. For example, at the corner, you can pass these two walls and the roof passing through that point. Then you can close this plane, and on the right here, these three planes can pass through point A, which is the origin. And to close that, I can make a cube to show the state of stress at point A. So in general, if I want to represent a stress at the point, I can define a cube like this, if this is axis X, Y, and Z, to represent the stress element for point A. For a given plane, suppose this plane. If you remember, we defined three terms of the stress. Two terms are tangent to the plane. We call them shear stress, or we label them with tau. And one stress term is going through the plane, perpendicular to the plane, that we call normal stress. So each plane is going to have three terms of the stress. Two tangent and one normal, which is perpendicular to the plane. So then we back to the state of stress or stress element for point A. For this plane, which is one of the face of this cube, I can define three terms of the stress, two tangential and one normal. The normal term is going to be this. I label it with sigma. The index or subscript of the normal stress is going to be the same as direction of this plane. So the normal vector of this plane is x, so I label this as sigma x. For this one, I can define one normal stress perpendicular to this plane, and the subscript is y because the axis of y is perpendicular to this plane. For this plane also, it's going to be sigma z. And for each plane, I can have two tangential, tau, tau. The first subscript is going to be the direction of the plane, which is x. Second one is representing the direction of shear stress, which goes up in y direction, tau xy. Same thing here. It goes in z direction, tau xz. Do the same things for the other two planes, tau y x, tau y, z. Tau zx and tau zy. So totally 9 terms of the stress can be represented in general for a stress elements at point A. So this cube is representing the stress element at that point. We can prove or we can show that the cross shear stress are equal to each other. So xy, tau xy is going to be equal to tau yx. In most of the case, we have these three. So the 9 terms is going to change to, in general, sigma x, sigma y, sigma z, 3 normal stresses, tau xy, tau xz, tau yx is going to be equal to tau xy, so it's not a new term. Tau yz, I should add it here. And here we have tau zy, which is equal to tau yz, and tau zx, which is equal to xz. So these are the 6 terms of stress to represent the stress for point A. Yes.
You said that they would usually be each other. When would they not?
I mean, these two, they are equal to each other, the cross section, they are going to be.
Always.
Yes. Yep. At least in the scope of this course that we are covering, they are the same. So in some special cases, we might have different, but it's out of the scope.
We've exceeded capacity.
Pardon?
We've exceeded capacity.
Right. Yeah, would you bring just one? I don't want to change the room because the recording facilities that it has, and it has 50 chairs, I believe, but we are 51.
No, you got 49.
49?
Yeah, there's 4 here.
Okay. 50, okay.
So that's the issue.
The missing one. All right, back to this. We can define something that we say stress tensor. Stress tensor is representing the stress element at a point. It's gonna be a 3 by 3 matrix. Sigma x. The first row is representing display. Sigma x, tau xy, tau xz. Second row representing the display. Sigma y is going here. Tau yx, which is equal to tau xy, so I'm just writing tau xy. And tau yz. And third row is representing the third plate, which has the term of sigma z, tau zy, which is equal to yz. So I'm just writing yz, and tau zx, which is equal to tau xz. So I'm just writing tau xz. So we call it a stress tensor. I have a slide for this that we will go over that shortly. But this is a definition of the stress tensor. Just represent the stress elements in a matrix form. Any questions so far? How many terms do we have here? 6 terms. X, sigma y, sigma z, 3. These two are the same, 4. These two are the same, 5. And these two would be the 6, which are here. Plane stress. If all stress in one plane are 0, we say that we are going to have plane stress. Suppose I say that all stress terms in plane Z would be 0. Then the cube is going to look like this. We have sigma x, we have sigma y, we have tau xy, we have tau yx, which is equal to tau xy, but all terms in this plane would be 0. So I don't have sigma z, so this normal stress is not going to show up. I'm not going to tau zx, so it means I don't have any tau xz, I don't have this shear stress, and I don't have tau zy, so I don't have this term. So the plane stress is going to look like this if all terms of the stress in one plane are 0. This can happen in this plane or the other plane. So I just have for plane Z. Now, if you look to this cube from front view, from this side, what you are going to see, you are going to see one square. One square. If I look from this side, if I look from this side, I will see sigma x, which is perpendicular to this line, and I will see tau xy is going up. Sigma x. Sigma y, I will see this, and I will see tau xy or yx, which are the same. So if I have a plane stress, I can represent the state of stress or stress element with one square, with these terms applying to the side. So if you want to finish it, if you have sigma x here, you should have the another sigma x in opposite direction. If you have tau xy here, you should have the arrow pointing down. Same things here, sigma y going down, and when it goes this way, tau xy should go this way. So this is the plane stress. If you don't want to work with a cube. So these are the same, and this sigma x we will see one square, but in reality it's a cube that we are looking from the front side. So basically this sigma x is applying in this plane, as you see. So it's not basically one real square, it's representing one cube. But it's easily, we can simply represent that with a square. Any question so far? All right. Now we want to see how the stress term is changing if we have if we pick different plane. So if I pick this plane passing through point A, and I look from top, I will see one square like this. The plane that I chose is this one. If I look from top side, I will see one square, and one force pointing, it's coming out of the plane. So we are going to have only normal stress, which is equals to the force dividing by area, if I pick this plane. So now I'm going to change the plane, and I want to see how the stress is varying by changing the plane. So now I pick this plane with the angle of theta, with the ground line. If I cut the bar through this plane, I'm going to have something like this. One force applying here. If we draw the free body diagram, the internal force applying in this side is going to be the same, but it's applied in opposite direction to make the summation of the force equals to 0, because we know that it's not moving. So internal forces should be P, and this angle is theta. So as a class activity, what I'm asking you to do is, if we have one force applied in this direction with the magnitude of the P, what would be the projection of this force in this direction and the normal direction of this plane? So basically, what would be force in tangential and force in normal direction as a value, as a magnitude of, as a function of P? So this is a simple static problem that I'm asking you to find the projection of force P in normal and the tangent direction. If this angle is theta, you see.
This is later. This is yeah. That is like
All right, number 34. Yes, what do you think?
Could it be the P normal is pretty much P cosine theta?
Normal, you said,
P cosine theta, or yeah,
and the tangential.
would be P sine theta.
Thank you. Any different thoughts? All right, that's correct. So, how can we find that? This is P. We are looking for these two vectors, and this angle is theta. So, if this angle is theta and this is 90, this angle is going to be 90 minus theta. So the projection of this force in this direction is going to be P cosine of this angle. So F tangential, which is tangent to the surface, is going to be whatever the magnitude of this force, which is P, the cosine of this angle, cosine of 90 minus theta. Cosine of 90 minus theta is going to be sine of theta. And F normal, which is this guy, is going to be P times sine of this angle. Sine of this angle would be this dividing by this. If I multiply by P, I can get F normal P sine of 90 minus theta, which is P cosine of theta. Everybody can see why it's normal is P cosine and tangent is P sine. Good. Okay. Make sure that you are following because we are going to go to the this one shortly. All right. Now, if this length is A and this length is 1, if I cut the plane at the angle of theta, what would be this length? You can simply say again, it's gonna be this. If this is theta, this length is A, this length is A. We are looking for this L, which is A dividing by cosine of theta. Cosine of theta is A dividing by L, A dividing by L. Then L is gonna be A dividing by cosine of theta. So I could find this length, which is A dividing by cosine of theta. Now I can find the normal term and the tangent stress term for the plane that I pass through point A with the angle of theta. For this plane, there are two forces applied. One is tangent to the plane, one is normal. The tangent is making the shear stress, the normal is making the normal stress. For the normal stresses, Fn dividing by area is, if you look from the top, is going to be this length times 1. The area is this length times the thickness, which is 1 inch. So that this length is A divided by cosine of theta times 1. And the normal force is P cosine of theta dividing by A divided by cosine of theta. It's going to be P over A cosine square of theta. P divided by A cosine of theta is going up. It's going to be P cosine square of theta. So the normal stress is going to be P cosine square of theta. And shear stress is going to be the tangential force dividing by same area. P sine of theta dividing by A cosine of theta. P over A cosine of theta sine of theta. So I could find the normal stress and the shear stress applied to this plane, which has the angle of theta. You remember for the plane which passing through point A, in this direction, we only had the normal stress, which was P over A, and the shear stress was 0. Now it has changed to P over A cosine square of theta for the normal, and the shear stress is going to be P over A sine square cosine square. Sine times cosine, not a square. So if I change the angle of theta, I'm gonna get the different value depending on the magnitude of theta. Now, if I look at normal stresses and I ask you at which angle we are gonna have the max max of sigma occurs at this is cosine. The maximum is gonna be when cosine square is 1. So at which angle we are gonna have 1? At theta equals to 0 or 180 degree. If you just have the plane with the angle of 0 or 180, you will get the maximum sigma. And minimum occurs at, this is cosine square. The minimum value is going to be when cosine is going to be 0. So at theta equals to 90 degree or 270 degree. And these two angles, if you cut something like this, passing through point A, you don't have any normal stress. Any questions so far? All right, let's look at the shear. 2 sine of theta cosine of theta is gonna be sine of 2 theta. If you remember, is sine of 2 theta is gonna be 2 sine of theta cosine of theta. So here we don't have 2, but we can say sine of theta cosine of theta is sine of 2 theta dividing by 2. So I replace this with the sine of 2 theta dividing by 2. I will get P over 2a sine of 2 theta. Now I would like to see at which angle I'm going to get the maximum shear stress and the minimum. Maximum shear occurs at, we have sine of 2 theta. The maximum value for sine of 2 theta, it occurs when sine of 2 theta equals to 1. So sine of 2 theta equals to 1. Then 2 theta should be either equals to 90 degree then theta is going to be 45. So at theta equals to 45, we are going to get the maximum shear stress because sine of 2 theta is going to be 1, and this is the maximum possible value for sine. For the minimum, if it gets negative 1, minimum sine of 2 theta equals to negative 1, 2 theta should be 270, and theta is going to be 135. Tau would be P over 2a, tau would be negative P over 2a. Here it's going to be sigma equals to P over a, sigma equals to 0. Good?
What is tau
Tau,
This is next to the 45 and the 35.
okay, yeah. If theta is 45, sine of 90 is going to be 1, then shear stress is going to be P over 2a. Make sense? I just have the value of the shear stress at its maximum value and the minimum value. The minimum value sine of 2 theta is going to be sine of 270, which is negative 1, negative p over 2. And similarly for the normal stresses. And you have, I summarized the results right here in this box. Theta 0 or 90, sigma is max or mean. Theta 45 or 135, tau is max and mean. 135 corresponding to mean and 45 corresponding to the maximum value. Any questions so far? The next step is moving from this to this. You have a plane stress element like this, but this cube is one of the infinite possible cases that we can have passing through point A. We can have different cube passing through this point. If I represent that with the angle of theta cutting this, what would be the normal stresses and shear stresses applied to that. So what I'm saying is, if we have this cube, this square, which is representing the plane stress, as you see up there. If I change the plane, how can I change the plane? Just cut it with the angle of phi. Just cut this with the angle of phi. I would like to find the normal stress and shear stress corresponding to this new plane. If the value of original squares are given, so we know what would be sigma x, what would be tau xy, sigma y, and tau xy. What would be the new sigma and shear stress applied to this? In previous years, I used to write the final equation, which represents sigma and tau as a function of sigma x, tau xy. But this semester, I decided to derive that to show you how we can get those values. It's not difficult. It's gonna help you to have a better understanding about how can we get sigma and tau. So this is our original plane stress. I represent it with a square. If I want, I can represent it by the cube, but it's easier to represent it with a square. So if I want to cut it by the angle of phi, pointing down. We would like to find the normal and shear stress corresponding to the new plane. Something like this that we derived here. Sigma as a function of, if you remember, P over A was the sigma. So it's going to be sigma for 0. So sigma is going to be P over A times cosine square. For shear stress, it's going to be P over A cosine square sine of theta. So we would like to find sigma and tau as a function of sigma x, tau xy, sigma y, and the angle of phi. So suppose this length is A. This length is A, and the thickness of cube is 1. So this is A. So if this is A, this length is gonna be A cosine of phi. This length of this triangle. And this length is gonna be A sine of phi. Sine of phi. So this is sine of phi A, this is A cosine of phi. If this length is A. Now, what I'm gonna do, I should set like the previous case. The summation of the force in x direction should be equals to 0. Summation of the force in y direction should be 0 as well. So in this part that I cut, this normal stress times this plane. I mean, this is one length. The thickness of the plane is 1. So this length times 1 times sigma x is gonna give me force in x direction. So sigma fx equals to 0 is gonna be negative sigma x because it's going to the left side, which is the negative side of x, times the area, A cosine of phi. This force doesn't have any x direction force. Tau xy is gonna have the force in x direction. Tau xy is going to the left side, is gonna be negative. The magnitude of the force would be shear stress times the area, which is A sine of phi times 1. Negative tau xy, A sine of phi. I don't write the 1, but basically it should multiply by 1 if you want to have area. So this sigma y doesn't have any x terms. This sigma times A is making force in this direction. So sigma times A, it's force. We are looking for projection of this force in x direction. If this angle is phi, I can show that this angle also equals to phi. So this angle is phi, this angle should be phi as well. Everybody can see why this angle should be phi. This is phi. If I draw a line parallel to the ground, this angle and this one should be the same. This angle plus this angle would be 90 degrees. This plus this one would be 90 degrees. And this one equals to this because two parallel, one passing through that. So this one equals to this part. And this plus this is going to be 90. So since this equals to this and this plus this equals to 90, I can say this one equals to this one. So this is phi. The projection of this force in this direction is going to be positive sigma times A cosine of phi. So it's going to be positive sigma cosine of phi times A. Tau. The magnitude is tau times A. But we are looking for its projection in x direction, which is going this direction. So this angle is 90 minus phi. We can show easily how to get 90 minus phi. So this times cosine of this angle is going to give me the x direction, tau times A cosine of 90 minus phi. 90 minus phi is going to be sine of phi. Tau A sine of phi. So it's going left side, so I'm put negative sign here. Negative tau sine of phi times A. This is for sigma in x direction. For y direction, I can have, for y direction, I do have tau xy going downward, negative tau xy. The area is a cosine of phi. What else? I have sigma y going downward, sigma y a sine of phi. The area acting to this stress is a sine of phi. And here, if this one is sigma times a, the y projection is going to be sigma a sine of phi. It's going up. And for this one, the projection is going up. It's going to be positive, but just change sine to cosine. Tau cosine of phi a. So equation 1, equation 2. Equals to 0. As you see, all terms they have a, so I can cancel out all a from both sides. We don't see any a terms in the next equation. Let me rewrite this again. Sigma a. I start from this one. Sigma a, not a. Sigma sine of phi plus tau cosine of phi minus tau xy cosine of phi minus sigma x sine of phi equals to 0. These two terms are the last two terms. And here I have these two terms first, and then I'm gonna write the first two terms. Sigma cosine of phi minus tau sine of phi. The first term is negative sigma cosine. Second term is negative as well. Question 1, question 2. Two equation. We are solving for sigma and tau. These are the terms that we are going to find, like this, sigma and tau. Two equation, two unknown. We should first get rid of tau, for example, solve for sigma, then back to the equation and find tau. How can I get rid of tau? Here I have tau cosine of phi, right here I have tau sine of phi. I multiply this by sine of phi and multiply this by cosine of phi. The first equation is going to change to sigma sine of phi, sine square of phi plus tau sine of phi cosine of phi minus tau xy cosine of phi sine of phi minus sigma x sine square of phi equals to 0. Second equation is going to change to sigma cosine square of phi negative tau sine of phi cosine of phi. This is positive, this is negative. If I add them up, I can get rid of this term. So I'm going to have only sigma. Negative tau xy sine of phi cosine of phi plus sigma, this is sigma y cosine square of phi.
That's a cosine, that's double sine. This is what happened. Maybe it was double cosine. I don't know. That's because I can't read it. I know what he's doing, but I don't know what he's multiplying by doing.
Alright, if you add them up, you can cancel out these two. You only have sigma. Sigma multiplied by sine square of phi plus cosine square of phi, which is 1. Minus tau xy cosine of phi sine of phi, they are the same. Negative 2 tau xy sine of phi cosine of phi minus plus sigma x cosine square of phi minus sigma y sine square of phi equals to 0. I just add them up. Sine square plus cosine square is going to be 1. So sigma minus 2 times sine of phi cosine of phi. It's sine of 2 phi. It's just we know that. So negative 2 is going to be negative tau xy sine of 2 phi. I would like to change these two as well. Cosine of 2 phi can be written as 2 cosine square of phi minus 1, and cosine of 2 phi also can be written as 1 minus 2 sine square of phi. We can write cosine of 2 phi in these two forms. Now find cosine square of phi is going to be, if you move on to the other side, cosine of 2 phi plus 1 dividing by 2. Plus 1 dividing by 2. And sine square of phi is going to be, if you move this to the other side, you will have 1 minus sine of 2 phi, sine square of phi. Cosine 2 phi dividing by 2. 1 minus cosine of 2 phi dividing by 2 is going to be sine square. I replace cosine square with that term, sigma x times 1 plus cosine of 2 phi dividing by 2 minus sigma y, 1 minus cosine of 2 phi dividing by 2 equals to 0. We are almost there. So sigma equals to, I keep sigma on the left side because I would like to find sigma as a function of the other terms. So sigma equals to positive, I move it to the right side, which is 0, positive tau xy sine of 2 phi plus sigma x dividing by 2 be, hold on. This should be positive. When I wrote from here, I forgot about because I missed something. This one should be positive. This should be negative. Or sigma x, don't change them, just sigma x. Where is sigma x? Right. So negative sigma x times dividing by 2, negative sigma x cosine of 2 phi dividing by 2 minus sigma y dividing by 2 plus sigma y cosine of 2 phi dividing by 2. This is positive, positive. And now these two can be written as sigma x minus sigma y dividing by 2, these two. Plus, these two have cosine of 2 phi, it's going to be sigma x minus sigma y dividing by 2 cosine of 2 phi. And last term is tau xy cos sine of 2 phi. And this is going to be sigma. Something like this.
Just so you know, it's 2:15.
I just finished. Sorry. So I found sigma, I will find the shear stress on Wednesday class.